Now that we have a good basic understanding about how sets work, we're going to look at how we prove set relationships, in particular the set relationships of subset and set equality. So in order to figure out how that works, we're first going to have to review definitions of what it means for two sets to be equal and what it means for one set to be a subset of another. Then we use these definitions to figure out how we will prove relationships between the sets. We'll set them up as if-then statements, so we know what we're assuming and what we have to show. And then we're going to demonstrate these techniques on a basic example. All right, so let's look at the definitions of subset and equality in sets in a way that makes them clearer to prove. And remember, what's clearer to prove for us means it tells us explicitly what we're assuming and what we're trying to show, so that proving them is in the form that we're used to doing. So let's suppose that A and B are sets. We say that A is a subset of B if whenever an element is in A, then it is also an element of B. And we say that A is equal to B if an element is in A, if and only if it is also in B. So if you look at the definition of a subset, you can kind of see the if-then. Whenever an element is in A is kind of the if part, then it is also in B. And then the set equality is an if and only if statement. So I just want to note that even though it's not explicitly stated in the definitions, there's an implied for all in there. So if we're looking at A as a subset of B, what we're saying is for all X in the universal set, and remember, whenever you're talking about sets, you also have to talk about a universal set that contains both of them. So we're looking at all X in the universal sets, and we're showing that for all of them, if X is in A, then X is in B. So in terms of how we're going to prove this, we're going to prove the statement if X is in A, then X is in B, with the understanding that X can be literally any element in the universal set. Except once we have the if part of X is in A, we're all of a sudden assuming that X is in A. So for the proof, in terms of what we're going to assume, what we're going to show, well, we're going to assume that X is in A, where X could be any element in the set, and then we're going to show that X is in B. Proving two sets are equal to proving A is equal to B is very similar. The only difference is it's going to be an if and only if statement. So again, it's an implied for all statement. We're looking at for all X in the universal set, X is in A if and only if X is in B. And then that means we're going to prove that X is in A if and only if X is in B, where X can literally be any element in the universal set. Now, this is an if and only if statement, so we're going to actually have to do two proofs for this one. So if we're trying to prove that two sets are equal, first thing we're going to do is the first part of the proof, which is we're going to assume X is in A and then show X is in B. That proves the statement if X is in A, then X is in B. Then we're going to flip that around by assuming that X is in B and then showing that X is in A. That proves the statement if X is in B, then X is in A. All right, so let's see how this works in an actual theorem. So we're going to show that the set of natural numbers is a subset of the set of rational numbers. Okay, and remember the set of natural numbers, those are the counting numbers, 1, 2, 3, 4, 5, etc. And the set of rational numbers is the set of all fractions of integers where the denominator is non-zero. So what we're going to do in order to prove this is a subset proof. We're going to assume X is in the natural numbers, and we're going to show that X is in the rational numbers. So remember, the natural numbers are the counting numbers, 1, 2, 3, 4, etc., all the whole numbers starting with 1. And then the set of rational numbers, that is the set of fractions m over n, where m and n are both integers and n is non-zero. And so when we do this proof, we're going to start with what we assume, which is X is in the natural numbers, but then we want to end with X is in the rational numbers. So we're going to this is one of those proofs that's, in this case anyways, a little easier to work backwards, so I'll show you how that works. By the way, this is not always the case that you're going to work backwards when you do subset proofs. It just happens to be useful in this case. So we want to end up with X in Q, and if we want to wonder, like, what's the step that comes before that? Probably the definition of Q, which means we want to show that X is the fraction of two integers, right? One on the top and one on the bottom, and we have to sort of fill that in. But, you know, X is a natural number, which is also an integer, and so if we put X on top, that means we can put 1 on the bottom. 1 is also an integer. So we have X equals X over 1, where X and 1 are both integers. From that, it implies that X is in Q. So, of course, in order to get there, we have to actually prove that x is an integer, but, whoops, wrong way. But we know x is an integer because all natural numbers are integers. So that's going to be our justification. And then, of course, we're going to start with x is a natural number. And so let's make sure the logic goes forward like it's supposed to. We start with assuming x is a natural number. Since x is a natural number and all natural numbers are integers, that means x is an integer. And we can write x equals x over 1. And note that x is an integer and 1 is also an integer. And then that implies that x is in Q because that's the definition of the rational numbers. All right, so the logic works there. That's our outline of our proof. Let's see what happens when we try to make it formal. So first of all, we're going to explain what we have to do to prove, especially in the beginning, because remember, you're writing for your peers. We may not be very comfortable with subset proofs, so we may need to do a little extra explanation. So what we need to show is that any natural number is also a rational number. In other words, we assume that x is in the natural numbers, and we show that x is in the rational numbers. Right? So again, we're being very clear about what we're assuming, what we're showing, and even, and you don't have to do this, but even in the beginning, give a little general explanation about how to prove one set is a subset of another, just to refresh in case your reader needs to know. Not required, but something that is generally a nice thing to do. So what we're going to do to prove as a subset, we're going to assume that x is a natural number. And then so since we're assuming that x is a natural number, which we were saying before, since every natural is also an integer, we have x is an integer, right? So that was the first step of the outline in our proof. The next step was to write x as a fraction. So note also that 1 is in the integers, and we're sort of thinking ahead because remember the two integers that we're going to be dividing are x and 1. Since both x and 1 are integers, the definition of rational numbers implies that x over 1 is in the rational numbers. So again, we're sort of laying the groundwork for our case that x is a rational number by getting the fraction equal to a rational number first. But we also have x equals x over 1. That's just the definition of division. And so that implies that x is in Q. X is a rational number. And again, just to let your reader know, that's what we were trying to prove, so that completes the proof. All right, so now you should try your own problems in the set of in-class activities that's on the PDF file included with this video, and it's called Introduction to Proving Set Identities.